Yesterday, before we get into this question, yesterday we finished with kind of talking about, or I showed you a question that dealt with like a fan blade, I think. Think about if I've got a fan blade. Apologize for my crude pictures here. Okay, so got your fan here, right? Okay, they want to know how fast is that fan blade moving in regards to a linear speed and an angular speed. Okay, so if I think about turning this fan on, is that going to be circular? Okay, so when they talk about a fan blade, now I think in the question they say a fan blade is 28 inches or something like that, or 52 inches or something, whatever. My assumption is that they're talking about from the center of the circle to the tip of the blade is 28 inches. That makes sense? Okay. Some people might, think this way. If I look at a fan that maybe is developed this way, where it's got 4 blades, or maybe the propeller on a helicopter, or not a helicopter, maybe a helicopter, or a airplane. I think one could argue that that distance there is the length of a blade. Does that make sense? Okay. But I think in your homework in WebAssign, they're talking about that as being the length of a blade. Okay. So when they tell you the length of the blade, I think they're telling you the radius. Okay. It's the way I would view it. But you'll see that question, and they're asking, they'll give you information about how fast that blade is rotating per minute. So they give you an RPMs, and they give you a time frame. So you can use these formulas we're dealing with, okay, and find angular speed and linear velocity. Another question they're going to ask is, you've got a saw blade, okay? When they talk about a saw blade, again, crude pictures. We're looking at something like that, right? Okay, and that's going to rotate very quickly. But they ask how fast is that tooth on that saw blade rotating, okay? What's the angular speed of that? And what is the linear speed of that? Is that the exact same idea as asking how fast the tip of that fan blade is moving? Yeah, okay. They may ask you, to be sitting in a chair on a Ferris wheel, and that Ferris wheel is moving around. Is that the same concept as the sawtooth? Same concept as the fan blade? They might say that you have been driving your car or your bike and you run over a nail, and you keep going, and they want to know how fast is that nail moving. Is that the same thing as these questions? All right. So all those questions, regardless of the context, they're asking for linear velocity and angular velocity, or angular speed, and linear speed. Those are just changing the story, but the problem is still the same. Is that okay with everybody? So you might see 3 or 4 of them kind of flip back and forth between that in your homework. Once you understand that it's really 3 or 4 of the same exact questions. This one here, example 7, says a woman is riding a bicycle whose wheels are 26 inches in diameter. The wheels rotate at 125 revolutions per minute, which a lot of times they're just going to say RPMs, and they won't say revolutions per minute. I note that unit is, or that rate is. It says find the speed at which she is traveling in miles per hour. I think that this is a good example because it allows us to use the fact that linear velocity is equal to radius times angular velocity, okay, or omega there. We can use that formula. Now, we don't have to use that formula. You can manipulate and work your way through without using that. But I think it's useful in this question to maybe address this formula. R stands for radius, right? What is the radius for our particular wheel? 13 inches. Okay. Now they also ask you in this formula to find linear velocity, we have to find omega. And if you remember omega, that is theta divided by time, right? Okay. Well, theta, if you remember theta, that's 2 pi, which is 1 complete revolution around the circle, right? Okay. Times in how many times those revolutions take place. So I'm going to write those formulas down, those components, those, that radius. And now I'm going to start seeing if I can determine what theta and t are so I can plug everything into this formula. Well, they tell us that the wheel rotates at 125 revolutions, right? That's what we're looking at, 125 revolutions. So can I say that my theta is 2 pi times 125? And that gives me 250 pi. Now, theta is always an angle, right? So the units here should be radians. Is that okay with everybody? So the theta is 250 pi radians. If I were to look at that and talk about that as like degrees, I always think it's maybe a beneficial thing to flip-flop, especially early on when you're trying to grasp an understanding of degrees and radians and how they compare. I would change that to maybe degrees and see what that is. And if I change that to degrees, I think it's 45,000 degrees. Okay, so you've gone around a circle a lot of times, right? And it traces out that many angles, that many degrees. Sorry, but we want to leave it in radians because that's what the formulas force your theta to be in. Okay, but I think it's always a good idea to have a comparison in mind of how big that is. The next thing we're going to do is say, okay, well, if I now know theta, if I know theta is 250 pi radians, and I've watched this thing, when it says revolutions per minute, does that per minute tell me a time? Yeah. I now have my omega, or my angular speed, to be 250 pi radians per minute. Okay. And when we find theta and we find omega, those two things are descriptions about an angle. So you need to leave the radian unit in there, right? So it's an angle per unit of time. So radians per unit of minute. Okay. So now we know our radius and we now know omega, right? Can I plug those things into that linear velocity formula? Can I come up here and say radius is 13 inches times then omega, which is 250 pi radians per 1 minute? Multiply that out. 250 times 13 gives me 3250. So you get 3250 pi inches are the unit up top. I've also got radians there, so I'll write that down, but we'll talk about it in a moment. And on the bottom, I've just got 1 minute, correct? Now, if I look at that, we have a linear velocity, a speed. So maybe the speeds that you guys are most comfortable with are like miles per hour, right? Okay, so we got something like that, but it's in inches and minutes. Do I ever have like miles, radians per hour? No. Okay. When we're talking about a linear velocity or linear speed, the radians are not a unit that we want in there. Okay. We talked about several times how they're dimensionless. They're a length divided by a length, so they're really not a component to our units when we're talking about this speed. So now we've got that as a final answer. Now, here's the thing. This is the reason why they do this. Obviously, that is a solution. That's how fast that thing is moving. But does anybody in their mind have a good understanding of how fast that is? No. We drive at 60 miles per hour on average, right? Probably. Jared, you got a little faster, don't you? Probably. Okay. You shouldn't. All right. So, it's probably better for us because of the units that we use on a regular basis and how they affect us in life to change this to miles per hour just to get a gauge of how fast this thing is going. If you lived in Canada, you'd probably put it into kilometers per hour, right? Because the units that they use are I just think it's ingrained in us a little bit more to understand what this means to us if we change it to a unit that or a rate that we're familiar with. So Let's change this to miles per hour. So when I find miles per hour, that's the units that I want left up on top are miles. The units that I need left in my denominator are going to be hours. And the way we're going to do that is through multiplying by conversions. Okay? If I look at this unit right here, this inches, it needs to disappear, right? Because I want the distance to turn into miles. So I'm going to put inches down here. Now they're going to cancel out. Do you guys know, is it common knowledge to know how many inches there are in a mile? No. Okay? It's quite a large value. But there is common knowledge of how many feet are in an inch, right? Or how many inches are in a foot. Okay? Either way you want. We can think about how many feet are in an inch, but that's going to give me a decimal up here, and that's just going to be kind of hard to deal with, right? So it's better to talk about how many inches are in a foot. If I do that, the inches are going to cancel out. Now I need the feet to cancel out, right? So I've got feet down here. Is there a direct link between feet and miles? Yeah. I'm always going to ask myself that question because we want to get from the distant unit that you're using right now to the distant unit that you want in an answer as fast as possible. So we're always going to develop that question, is there a common knowledge conversion from one to the other? So now if I multiply all that stuff out, I'd have an answer in miles per minute, right? Still probably something we're not comfortable with understanding, okay, or comparing our values to. So let's try to get this minute to go away. So if I get that minute to go away, it's got to have minutes in the numerator somewhere, right? So they will disappear. Is there a direct link between minutes and hours? Yeah, that's common knowledge, right? So now think about how this happens. If I multiply straight across the numerator, you're going to be left with the miles that you're looking for, right? If you multiply straight across the denominator, you're going to be left with the hours that you're looking for. So my answer will be in the correct units here. All right? Now, because of the associative property of multiplication, could I have put maybe that fraction and that fraction? Could I have flip-flopped them? Yeah, okay. And I can flip-flop any of these four things and put them in any order that I want to. So just because we canceled the distant unit first doesn't mean you have to do it that way. You could have canceled the minutes first. But now once I've got the units right, I go back in and I plug in the numerical components. So for every 1 foot, I have 12 inches, right? For every 1 mile, I have 5,280 feet. And for every 60 minutes, I get 1 hour. Okay? I think that's the best thing to do. When I multiply that out, I'm going to get, obviously, miles per hour. We know that's going to be true. But then multiplying all of that, make sure that when you type it on your calculator, because when we multiply fractions, you go straight across the top, right? Get that product. And then divide that by the product straight across the bottom. So make sure that you put things in parentheses. I'll go 3250 pi times 1 times 1 times 60. And then we'll divide that by, across the bottom, 1 times 12 times 5280. So 12 times 5280. Make sure that's in parentheses. Hit enter. And I get about 9.67 miles per hour. And that's probably a little bit more of a number that we can grasp and understanding for, right? Okay. If I say something's traveling 10 miles per hour, you can visualize that. If I say something's moving 3255 inches per minute, okay, maybe you can't visualize that, but they are moving at the same pace. So someone can do. Every once in a while in WebAssign, they're not going to tell you to round. They'll just leave the question blank, and they won't give you any rounding hints or directions. That means don't round it. That means leave it as an exact answer. Okay, so you would multiply that numerator out, leaving pi in there, multiply the denominator out, and then you'd start canceling like factors and leave it as a reduced fraction. Okay? So just be cautious of that. If they don't tell you how to round, they don't want you to round. They want exact answers. Okay? Now I did mention, let me just write this real quick. If I go 3250 pi over 1 minute, okay, now I could have also said, we had feet and inches here, right? Those were our units. Could I have done this? Could I have said that for every 1 inch, we have, let's see here, 0.08333 repeating feet? Is that the same conversion as 1 foot over 12 inches? Yes. Okay. Now, the thing about that is that 0.083333 number, you got to round that at some point, right? So it doesn't really make a whole lot of sense to use that conversion rate. Okay. It makes more sense to use the 1 over 12. Allow yourself to use the integers instead of the decimal version. Is that all right? Okay. Sometimes if we're going from one system to the next, we might have to use, like, for instance, with one inch is equal to 2.54 centimeters. Okay. I'm going to venture to say that 2.54 centimeters is a rounded number, right? Okay. So we have to use that. But if we can avoid using rounded numbers in our rates, our ratios, that's going to be a good idea. Okay. Is everybody okay with that? Okay. That assignment 5-1, day 2, I want that to be due tomorrow. I'm going to open up 5-2 for you at some point today. That's not going to be due until sometime next week. Okay, probably Tuesday next week. But this is not a extremely difficult section if you remember a little bit of stuff that you learned from geometry. Okay. Now I know you use this stuff in Algebra 1. We talked about in geometry. You used it a little bit in Algebra 2. So this is going to be the 4th year in a row that you've talked about some of this stuff. So hopefully I know we're going to have to kind of bring it back and relearn it maybe to some degree. But eventually it's going to be something that you guys realize, well, we've done this before. There's going to be part of this course is looking at how our trig ratios all relate to one another, okay, and all the different types of relationships that occur. And these are what we refer to as the 6 trig ratios, and they are predicated off of an angle, okay. So you have to first decide what angle you're looking at. And if you remember back to geometry, we did this. I gave you this picture right here, okay, and we identified a particular angle that we were interested in. We're interested in that angle theta there, all right, and then we started labeling the sides that were opposite to theta, okay, so across from theta. We wanted to label the side that was next to theta or adjacent to theta, and then obviously our hypotenuse, okay. Now this is something to always think about. Your hypotenuse is adjacent, right? It is adjacent to theta, because adjacent means right next to, but being a hypotenuse takes precedent over being adjacent. All right, so just keep that in mind. I think people that struggle with this, and it happens quite a bit early on, is that they mess up where that adjacent spot should go. So my thought is always find your hypotenuse, because that's really easy, right? And then I think the easier one is to find the opposite then, okay? And then by default, adjacent has to be kind of where it's at right now. And now that changes based off of the angle that we look at, right? So if that's theta, but now maybe I want to look at beta up here. For beta, this would be opposite, right? This would be adjacent, and this is still going to be my hypotenuse. So it's all these side lengths are dictated by the angle that you're interested in, okay? And this only works right now in right triangles. We have to have a right triangle to be able to use this. And if you remember from previous years, what was the phrase that we used for these ratios? SOHCAHTOA, okay? So sine is opposite divided by hypotenuse. Cosine is adjacent divided by hypotenuse, and tangent is opposite divided by adjacent. Okay. Those are the first three trig ratios that we've introduced, that we've talked about the most throughout the last maybe 3.5 years or so. But I want to talk about what they mean to us. Okay, so grab your calculators, and I know we're running short on time, but I want to at least give you a little bit of an understanding of what is really happening when we talk about these trig ratios and why they are what they are. Okay, your trig ratios come from right triangles. Okay, and any two right triangles that share an angle other than the right angle are going to be similar triangles. Okay, if you remember back in geometry, we had angle similarity. Okay, which said that if just any two triangles in general, we're going to do with right triangles. Any two triangles have two congruent angles, then that means that their side lengths are proportional. Okay? It means their side lengths are in the same ratio to one another. All right. So if I look at, let's say, this triangle right here. Okay. Now, before we do anything, I'll preface that we've got some rounded values up there. That angle gamma down there, it says 26.5651. Let's round it to 4 decimals. The 8.9443 is rounded. So when we do this, there might be some discrepancy in the rounding that occurs on your calculator, but it's going to be out 4 or 5 decimal places. Okay? So the practice here is I want you to view some relationships that should be true. And if we use 15 decimals or the exact values here, there will be absolutely no discrepancies in our solutions here. But what I want you guys to type in, just go to mode first on your calculator. So hit the mode key. And now, the reason I know I need to be in the correct mode is because I'm interested in working with this angle measurement, and right now it's in the unit degrees, right? So because things are in degrees, we want to make sure that our mode is in degrees, okay? And I just want you to type in sine of 26.5651, and then hit enter. And you're probably going to get something in the ballpark of like 0.5 or 0.4, is that right? 0.6 maybe? What'd you get? 0.45, okay? So that means that if I have a 26.5651 degree angle in my right triangle, the opposite side divided by the hypotenuse should give me that 0.45 number. So take 4, okay, so now what I want you to do, I'm going to take this opposite side, I want you to divide it by that hypotenuse. So take 4 divided by 8.9443. Does that give you the exact same decimal that the sine of 26.5651 gave you? Yes, right? Okay. Does that make sense? Okay. So the sine of that angle is telling you the ratio of those side lengths. Now here's the thing. It doesn't matter how big that triangle is. So let's look at this triangle. Would you agree that triangle is different? Okay. But does it have a right angle? So the red triangle and the blue triangle have a red angle, right? Do they both have this angle here that I called gamma at 26.561, right? So the red triangle and the blue triangle are similar. So now what I want you to do, there we go. I want you to take 2 and divide it by 4.4721. Take the opposite side of that triangle and divide it by that triangle's hypotenuse. What do you get? You get the same decimal, that 0.45 number, right? Okay. As long as I maintain that 26.5651 angle, and I maintain a right triangle, regardless of what the opposite side is and what the hypotenuse is, they will always divide to give me that ratio, that sine of 26.5651 was giving me. Is that okay? So these, are we going to use that, talk about that every day? No. Okay, but what I want you guys to understand, and this is something that hopefully mathematically you've maybe experienced or that you will experience, is that you start going through things, you start using these functions that maybe seem kind of like arbitrary or not really knowing where they come from. I want you to, as you're going through this course, and you think about why am I doing what I'm doing, or why is what I'm doing working, it's because of that. Okay? Whenever you're using sine, cosine, tangent, those things are occurring. The last class we got a little bit further with talking about those ratios on the bottom. So we'll pick up with that stuff tomorrow. But those are just the reciprocals. Okay? Maybe you've seen them, maybe you haven't. We got more than a 2-minute discussion about those things, so I'm going to kind of stop. But your calculator does not have those buttons. Your calculator does not have the CSC and SEC and COT, okay? Secant, cosecant, cotangent. So we're going to have to use our understanding of them being reciprocals to help us evaluate when they want what the cosecant of an angle is, okay? So we'll talk about that tomorrow. That's what we'll start off with. Like I said, I'll open up 5.2. Don't know how much you'd be able to get through with that. I don't really didn't do any examples, just kind of logic type stuff here. But I'll open that up. That won't be due till early next week, Tuesday or Wednesday. But do have the 5.1 day 2 due tomorrow.